Hello, in this video we're going to solve some common physics problems using trigonometry, law of cosines, law of sines, and some vectors. In the first example here we have a helicopter pilot who needs to travel to a regional airport 25 miles away. She flies off with an actual heading of northeast at 16.26 degrees with an airspeed of 120 miles per hour, and there's a wind blowing directly east at 20 miles per hour. And so in the first thing we're going to do in all of these problems is we're going to draw some vectors. We'll call the y-axis the north-south axis, and we'll say this is due north, and we're going to say this is due east. And so she flies off with an actual heading, this is not to scale, but an actual heading of 16.26 degrees. And then there is also a easterly wind there at 20 degrees. We're going to call this velocity with respect to the ground. We're going to call this velocity of the wind. And then over on this side, we've got velocity of the helicopter. We know that is 120. Velocity of the helicopter is 120. And we know that, what else do we know? That's all we know for right now. We're going to call this angle here theta. Right, and in order to find the compass direction, this one here, we're going to call this our unknown. We need to find that for letter A, determine the compass heading that the pilot needs to reach her destination. We're going to use the law of sines here. And so if we know 16.26 degrees, we could carry out this easterly vector and make a right angle with the y-axis, in which case we know this is 90 degrees. And so 90 plus 16.26 plus this angle here is equal to 180. That makes this angle 73.74 degrees. And now we can use the law of sines. So remember, sine A over A equals sine B over B equals sine C over C. And so we've got sine theta, this angle here in this triangle of vectors, right? We've got the actual heading, we've got the compass heading, and then we've got the wind, right? So angle theta there is opposite magnitude of 20, and then that's going to be equal to our angle here, sine 73.74 over the opposite side, which is 120 miles per hour, and we're going to multiply by 20. We get sine theta is equal to 20 sine 73.74 over 120. We'll take an inverse sine there to find our theta, which is 9.21 degrees. Right, so if theta equals 9.21 degrees, then A is equal to 16.26 degrees minus 9.21 degrees, or 7.05 degrees, and we could say this is northeast. Okay, on to B, we're going to use the law of cosines this time. Again, we've got that triangle, we've got that triangle of our three primary vectors. We've got the compass heading, we've got the wind, and then we've got the actual direction here. So we know that this angle here is 9.21, and we know that 16.21 plus 9.21, 7.05, 16.26 equals 7.05 plus 9.21. We know that angle. We know this angle over here is equal to 73.74. And so then we can just do a sum of our angles in a triangle to find this one here, 73.74 plus 9.21 plus 97.05 is equal to 180. And so we're going to say, again, this is VG, this is VW, this is VH. So VG is equal to, remember from the law of cosines, we've got the other two sides squared, sum of the squares of the other two sides, minus 2 times the other two sides, times cosine of the angle opposite the side we're looking for, 97.05, and that all gives us v with respect to the ground velocity over ground of 124.05 miles per hour. And that's like the 120 that the helicopter is going, plus the wind is pushing it in the x direction or in the easterly direction, so it actually adds speed because she is trying to go easterly anyway. If she was trying to go due north, then it would not add speed, it would be a different situation. But since she is already trying to go easterly, then it makes her go faster. And so how many per minute is that? That equals, I'm going to divide by 60, 2.07 miles per minute. And we've got 25 miles, right? So we got 25 miles. 25 miles divided by 2.07. We're going to say this trip takes about 12 minutes, rounded to the nearest minute. Next one. Box problem, you'll see a lot of these in introductory physics courses. Also, this is directly out of a pre-calculus book, so we're using a lot of the same techniques. Physics is basically just applied math. So a 20-pound box sits at rest on a horizontal surface. We have static friction here. There's an equilibrium of forces since it's at rest. There's friction between the box and the surface. That's why it doesn't slide down the ramp. One side of the surface is raised slowly to create a ramp. The friction force opposes the direction of motion and is proportional to the normal force Fn exerted on the surface of the box. Fn is perpendicular to the ramp. The proportionality constant is called the coefficient of friction, mu. When the angle of the ramp, theta, reaches 20 degrees, the box begins to slide. So at 20 degrees, we no longer have an equilibrium of forces. We have kinetic energy in the downward motion. Find the value mu to 2 decimal places. So we're just looking at the, we're looking for the static friction at 20 degrees, or just below 20 degrees as it might be. And so we've got our ramp here. We've got an angle of 20 degrees. Got a box, got a normal force, Fn. You might call this a free body diagram. We're going to call this F, force of friction. And then we've also got the force of gravity times the mass, which is also known as the weight. And so we can also draw this triangle. We're going to take this out here. We've got the downward force, F of weight, and then we've got the normal force going in this direction here, right? F normal. And then we've got the force of friction here. And so this makes a right angle. This angle is 20 degrees, same as the inclined plane, because what we're doing here is making that same triangle, and so we're going to have one line. Let's see, these would be parallel. This here is parallel to that. And so if this is a right angle, then this is a right angle. And so this is 20 here. And these two triangles are similar. We've got 20 here and 20 here. And then this angle would be equal to this angle up here. Alright, so we've got our free body diagram. We've got our forces all mapped out here. We're looking for the force of friction, or the coefficient of friction actually. We know the magnitude of the weight is equal to 20 pounds, and so let's just apply some of our rules here. We know that sine of the angle opposite the friction force, sine of this angle here, 20, is equal to the magnitude of the friction force that's opposite over hypotenuse. over the force of weight, which equals 20. And so we could say 20 sine 20 is equal to the force of friction, or the magnitude of the friction force is equal to 6.84. Units are not terribly important for right now. And then let's figure out whatever the normal force is here. The cosine of that 20 degrees adjacent over hypotenuse is equal to the magnitude of the normal force over, again, the hypotenuse is the weight, and so F, the magnitude of the normal force, is equal to 18.79. And from our physics equations, we know that the friction force is equal to mu. We're going to call this the static friction times the normal force. And so we're going to divide by, I suppose we can do it like that. We're going to say mu is equal to the friction force, which is 6.84, divided by 18.79, or mu, that's a terrible mu, is equal to 0.36. Alright, two decimal places. So again, physics is basically just applied math. Now, people spend a long time figuring out all of these equations, and there's a lot of laboratory work, and there are definitely some special rules in physics, but without mathematics, physics would just be philosophy and a lot of guessing. So in this one, static equilibrium, show the following graph, the force needed for the object P to be in static equilibrium. Static equilibrium is when all of the forces are in equilibrium, or when the force in each direction is equal. And so what we're going to do is we're going to figure out where these lie on the coordinate plane, 1, 2, 3, 4 up, and 1 to the left. We're just going to say P is at the origin, so we're going to got -1, 4, and then we're going to move 1, 2, 3 to the left along the x coordinate, along the x axis. So we got -3, 0, and 1, 2, 3, 4 down on the y-axis is 0, -4, and then 2 down and 4 over, 2, 4, -2. And then we're just going to add all of these up. Now in vector language, our x-axis, x direction, is actually I, and then our y-axis turns into j. Don't ask me why, that's just how they did it. And so we're going to add up all these x components. We'll start here, we got -1, and then we'll just go clockwise, +4, +0, -3. -1 plus 4 is 3, -3 equals 0i. That's good, so we're in equilibrium on the I side, or on the x side. And then we're going to add up all of our y components. We've got 4, -2, -4, +0, and that gives us 4 minus 4, that gives us -2j. And so we're not in equilibrium here. In order to balance out these forces, we need to go in the opposite direction of -2j. So we're going to draw a new vector, a new force headed up to 0, 2, and that one will put us in equilibrium, which means all of the forces in all the directions. Here we have only 2 dimensions. They're all equal when we sum them together. That one was pretty easy. Take a look at the next one. Braking load. Well, this is pretty important if you want to park on a hill, if you want to be a car designer, if you want to install brakes or design brakes, or just do some physics problems. Toyota Sienna, I don't know, did the textbook authors get paid to plug this model and make in here? I don't know. But any car with a gross weight of this many pounds is parked on the street with an 8% grade. 8% is the degree of the hill. See the figure, find the magnitude of the force required to keep the Sienna from rolling down the hill. What's the magnitude of the force perpendicular to the hill? Perpendicular to the hill, that's going to be our normal force, right? That's our normal force if you remember from the other free body diagram. And so let's draw ourselves another FBD, free body diagram. We've got a right angle here, we've got 8 degrees here. And so basically we can just draw this the same as the box from before. And we've got a weight. Now in reality the center of mass on the car will not be exactly in the middle, but it doesn't really matter for now. In a lot of physics problems we kind of ignore certain elements of reality. So we've got the normal force here, which is again perpendicular to the hill. We've got the force of weight, which is 5,300 pounds. FW equals 5,300 pounds. We're working in imperial units. The textbook did say global version, but we're working in imperial units, so that seems kind of funny to me. Alright, so we've got a right angle there, and so remember from our previous example of the box, this angle at the top is going to be equal to the angle here, and that's just given some basic geometric theorems and proofs and postulates and things. And so what we're looking for is the normal force and the friction force, or the braking force. We're going to call this the braking force. We know one of these forces, we know both of these angles. If that's 8 degrees, this is 82 degrees because we've got a right angle over there, but we're not even going to need that. We've got cosine 8 degrees is equal to the magnitude of the normal force, right? Cosine is the adjacent over the hypotenuse over 5,300. And so we get the magnitude of the normal force is 5,248.42 pounds. Easier than you thought it was, I'll bet. And again, quite simply, opposite if we're looking for the braking force. The braking force, FB, force B, the magnitude thereof, over the hypotenuse, or 5,300, is equal to the sine of 8 degrees multiplied by 1,500, and we get the magnitude of the braking force is equal to 737.62 lbs, pounds. Okay. Pretty simple. Pretty simple. On to the next example. Alright, so we got a 1,200 pound chandelier. Chandelier is a light fixture, for those of you who don't speak French English. Chandelier is to be suspended over a large ballroom. So we've got a big room, we've got a chandelier, we've got some lights up above it. Chandelier will be hung on 2 cables of equal length, whose ends will be attached to the ceiling 16 feet apart. So we're going to have an isosceles triangle here, we already know that. We've got a ceiling, and then we're just going to draw a box here for our chandelier. And we're going to say, here's one point, and that's going to connect to the box there, and then to another point on the ceiling. These two are of equal length. And then we're going to drop an altitude here so we can make our right angle. And then we also know that this is 16 feet between the 2 anchor points. And so when we drop that altitude, we get 2 8-foot segments here, 8 feet and 8 feet. And so we are also going to say that we have some vectors here. Here's our force of the, I'm going to say tension I. I'm sorry, that's the J direction. And then we've got force of tension in the I direction. We've got the same thing over on this side. We've got the force of tension in the I direction and the force of tension in the J direction. Remember, Y turns into J and X turns into I when we're dealing with vectors. And then we've got the force of weight, which is equal to 1,200 pounds. 1,200 lbs. Right, and the chandelier is hung 16 feet apart, 16 feet from the ceiling. And so we've got 16 feet here. All right, and so now we can use tangent. Let's find this theta here. Call that theta. We're going to say tangent 16/8. Tangent, remember, is opposite over, tangent theta equals 16. Tangent is opposite over adjacent, so katoa. Opposite is 16 feet, adjacent is 8 feet. Tangent 16/8 is what will give us our theta here. So tangent 16/8, tangent theta equals 2, and so we're going to do an inverse tangent of 2, and we get, that will give us our theta is equal to 63.44 degrees. Now that's what we need to find these forces of tension here. We can say this is also theta because we've got two parallel lines here intersected by the same line. We've got alternate interior angles. And so in order to find our J direction, well, I suppose we don't even need to do that. We're just looking for the minimum tension on each cable. We don't even need to do all the F and J, the J, T and J right now. So we're going to use sine. We know that, let's see, f of t. I'm just going to call that f of t. And that's holding the chandelier up. And so sine theta is equal to 16 feet. If we use this as theta, here's the opposite, 16 feet over f of t, force of the tension there. And so, excuse me, nope. 16 is the dimension. We're looking for the magnitude. So this is equal to the f of w, which is 1,200 over f of t. And so we get f t equals 1,200 over sine 63.44. And that will give us 1,341.58 pounds. But remember, we need to divide by 2. Got 2 cables. And so f of t for one cable equals this divided by 2, or 670.8 pounds, lbs. And that is the minimum force. Now, if that chandelier swings ever so slightly, then the cable may break. So you want to have a cable tested at much higher tension than that. But that is the minimum tension. Okay, last problem. Almost the same, but we've got different angles here. Different angles this time. Static equilibrium again, same as our chandelier. This is basically the same problem, but you'll notice we have, instead of the same angle, we've got different angles here. And so we want to know what's the tension of each of the 2 cables. We can't just divide by 2 this time. We've got different cables with different tensions. And so let's start with our ceiling or our beam there. And then we've got a triangle. Some mass at the bottom of it. And all they give us is our angles and our force of weight. So we've got the weight is equal to 2,000 pounds. We've got 40 degrees here, 30 degrees there. And so what I want to do is start by drawing force or vector diagram here. We've got Fw for weight. We've got the right cable and the left cable. Right, and then here we have an angle of 40 degrees. And then that means that this is equal to 40 degrees. Here we have an angle of 30 degrees. And that means that this is 30 degrees. And so we're going to see that this angle across the x-axis is equal to 180. 180 minus 30 is 110 in here. And so that's going to be important when we look for the force on the left. We're going to say the force itself is equal to the magnitude of the force, that's the number of pounds, times, we need the I and the j directions. Cosine 140I. Cosine 140I, because we're working with adjacent over hypotenuse. Now adjacent is way over here. We're going to use for like the unit circle, we start on the positive side, we work counterclockwise back around to the x-axis, and so we're going to measure angles from the x-axis on the right over to the left. We're going to have to add our 30 degrees for that first vector there, and then the measure between those two vectors to get our I direction. So we want to call this 140 degrees and not 40, because again we're starting from the right. And then we're going to add to that sine of 140j. Remember, sine is opposite over hypotenuse, and so our j direction is this opposite here. And then that equals, same thing, magnitude of force L. And it's roughly equal to negative 0.766 I plus 0.643 J, right? And we're going to have to come back and recalculate these so we can be precise later, but this is a rough estimate. I rounded off to 3 decimal places there. And so we could say that FL, we can distribute this out. We can say FL, force on the left, is equal to the magnitude of the force times 1 cosine 140I plus the magnitude times sine 140j. Okay, so again, we need an x component and a y component, or an I component and a j component. When we're working with vectors, the force on the right, we're going to do the same thing, FR. In this case, we've got cosine 30, again starting at the x-axis, moving upward in a counterclockwise direction to our vector here. We get 30 degrees. That is our I component, cosine 30I plus sine 30j. And then this is roughly equal to 0.866 times that magnitude, FR, plus, it's exactly 1/2 FR. Again, this is I, J. Okay, so we need to bust these up. Very important that we bust these vectors up into their x and y components, or their f and j components. And then we know that FW is equal to negative 2000 J, because it's only going in the y direction. Alright, so if we are in static equilibrium, then we know that all of the forces are, when we sum them, they equal 0. FL plus FR plus FW equals 0. And that also means that all of the forces in the I direction equals 0. the sum of the forces in the I direction equals 0, and the sum of forces in the j direction equals 0. And so we're going to say, we're going to take these values here, the I values, set them equal to 0, and so we've got the magnitude of FL cosine 140I plus FR cosine 30I equals 0. Now we're going to solve. We're going to solve for FL and substitute into our second equation. We've got a set of simultaneous equations here in case you didn't notice, and so we get the magnitude FL is equal to I solved for FR in my notes here. Magnitude FR is equal to FL cosine 140. We got negative FL cosine 140 over cosine 30. Again, and that's the I. And so we're going to take and substitute that into our second equation here. We're going to add up the j components. And so we got this one, and this one, right? And so what we'll get is, we've solved for FR, we've got FL, sine 140 plus FR sine 30, but that equals FL. So it ended up that this was a lot easier to use, it was simpler to use decimals here, and what I'm going to do is use decimals just to expedite the process here. So we got FL times 0.643 plus 0.885 over 2 minus 2,000 equals 0, so this equals 2,000. And then going back to our sine cosine values, FL is equal to 1843.21 pounds. And again, take that FL value, substitute it back in to find FR. FR is equal to, we're going to get negative cosine 140 over cosine 30 times 1843.21, or 1630.41 pounds. All right, so main idea here, physics problems are just applied math, and when we're working with vectors, we need to remember to start our cosine and sine measurements from the right hand, working counterclockwise around the unit circle. Sometimes we need to split up those f and r, or we need to split up those I and j components of vectors, which we can use using sine, which you can find using sine and cosine. Remember, sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is the opposite over adjacent. And by using the axis, y-axis and x-axis for north-south or I and j components, then we can make right triangles relatively easily, so we can solve these vector components, these vector problems, using simple trigonometric ratios. Okay, thank you.